Hi, welcome to this particular module, and in last module what we have seen atrial fibrillation, right, and now we know what exactly atrial fibrillation is, right. It is a heart disease where your heart starts pumping unevenly. So, actually that unevenness of pumping or heart beating is due to misfiring of signals, and then we have seen through video, right, that what is a procedure or what are procedures to cure this particular problem. Through this interaction and through the videos and through the notes, we understood that a tool that is called catheter is used to cure this particular disease, and that is how it is done, that when there is a misfiring of signal, first a catheter through a small incision is inserted into the body of a patient, and that catheter goes to the area within the heart where the electrical signals are misfiring. That catheter we call it as a electrical mapping catheter, right, so that we can know which area within the heart is misfiring. Now, once we have this electrical mapping, then the clinician will insert or the surgeon will insert another catheter for ablating that particular portion. So, when you talk about ablation, ablation is burning of tissue, that is a heart tissue where the misfiring of signals are occurring. So, that is the ablation process. So, that ablation can be using cryo, there is a cryo ablation, or it can be used it can be done using RF. So, RF is what? Radio frequency ablation. Now, in both the cases you are heating the tissue. So, when you heat the tissue will burn, right. If you burn the tissue, the current cannot pass, that means the signals will not pass. That means we think that the misfiring of signals has been cured, but it is very important to know the source of the signal, because it is not a uniform directional signal or large number of signals that is coming, like in the case of arrhythmia, right. In this particular case, the formation of signals is extremely non-uniform. It is very difficult to find a source of the signal. So, if you can burn that source of the signal, then the recurrence would be extremely low. Recurrence means a patient would have the same episode after going through surgery within few days, right. So, another way, there are several parameters that we observed, right, last time, including power density, what is the lesion size, right, what is the contact force, whether it is a irrigation catheter or non-irrigation catheter. So, lot of parameters are involved when you are talking about atrial fibrillation. We are interested in contact force because contact force is very important. Why? So, contact force. So, when the catheter touches the heart, what touches the tissue of the heart, right, how much force the surgeon is applying is very important. If the force is less, then the ablation will not be proper. If the force is more, then the other areas which were not misfiring will get burned, right. So, if the force is less, recurrence rate is higher. If the force is more, the burning of the unwanted region will happen. So, to have the optimized force, there are catheter force sensing techniques, and we have used we have seen yesterday a tachycac catheter and a thermocool, right, thermicool or thermocool, actually it is thermocool catheter. We have seen both these catheter which are right now used in surgery. Now, our idea is to design a catheter that can perform electrical mapping as well as ablation together. So, yesterday we discussed sorry we discussed this catheter, right, a newer design where it will open, the tome will open and a catheter within it. So, this external, this tome will have, through this tome we can give the RF frequency, right. We can also have make it conductive. So, the length of the tip increases, right, So, this particular section can give the can be used for RF ablation, while when this tomb opens, this thing opens, right, opens up, at that time the another catheter from within will come out, and that will be used for electrical mapping. That is our idea. Anyway, so you can design your own catheters. So, you see, this is a open problem. I want you guys to not only learn micro engineering or clinical applications, but I also want to think, right, think novelty. The things that we are learning this subject in this particular course are the things that are, most of the things are open problem, right. You can design, you can start working on this, you can start performing research, and if the idea is novel, you can have your startup, right. There are beautiful schemes from government like Make in India scheme, right. So use this kind of initiatives to design and to come up with a novel idea, novel technologies that can be implemented not only in clinics, but everywhere else with the knowledge of your this particular subject. Now, this particular subject is a part of the knowledge. You have to acquire other subjects, knowledge from other subjects as well, to form a complete setup, right. But like I said, if you know micro engineering, if you know microtechnology, then you can collaborate, you can integrate with lot of subject experts, right, starting from clinicians to a chemical engineer, to a mechanical engineer, to a robotics engineer, there is, to a biologist, there is a unlimited access to you, right. Learning this course, learning microfabrication, learning MEMS, learning the fab lab technology will give you unlimited access to collaborate, right. We will not make you an expert in all the subject, but will help you to work with someone, right. Working together, you can make cool devices. Working alone you can, but working together, it will be a really nice experience. Try sometime, right, to work together. Of course, I am sure that till now you guys have tried working together concept, right, other when we are preparing the homework or assignments, or it is about preparing for exams, right. We read together, we share ideas. So when you work on a research problems together with the interdisciplinary ideas, the results would be amazing. So coming back to our catheter problem, so this is a design that we have been talking about. What kind of force sensor you can use, right. This is one example of a force sensor. So, and how this force sensing mechanism would work, right. So, what you can see is if I apply a normal force, then there will be displacement, because of which you can measure the change in the capacitance. You can see the change in the capacitance. So, one way of measuring the force would be to have this kind of sensor. If the force is in this particular direction, which is shown here, again you will see the change in the spacing between the electrodes, and you can see the change in the capacitance. But this is only one way. There can be capacitive force sensor, that can be piezoresistive force sensor, that can be cantilever, there can be strain gauges. There is unlimited design for force sensing. Now, when we talk about force sensing, again another design, right. When we talk about force sensing, what kind of force sensor sorry what kind of force sensor we want to design, and here you can see a 3D force sensor attached to catheter tip. Observe it carefully, observe this section carefully. We will be talking about this section. So, what you see here? You see here a 3D MEMS based force sensor, right, and on this 3D MEMS based force sensor we have force sensor on 5 surfaces of cube. If you have a cube, how many surfaces of cube has? 1, 2, 3, 4, 5 and 6, right. Sixth surface is attached to the catheter here. So, on 5 surface we have 4 sensors, right, that is why we say 3D. Anyway, this is just a concept, right. Can it be actually implemented? So, for first to implement something, once to design something, you should start somewhere. So, this is a force sensor that we developed earlier, and we tried to measure we try to calibrate it with the actual force sensor available or commercial force sensor available in market, and I will talk about the results in the following slides. But the idea is that if you have force sensor on the catheter, can it be used for measuring the catheter contact force. Now, here what you see is a house fly. You can see a house fly, right. A house fly is sitting on the sensor, right, and the interest of making the house fly sit on the sensor was to measure the weight of a house fly, right. It is a strain gauge, it is a flexible material that we have used, again it is PDMS, right, on which there is a strain gauge, and on the strain gauge there is a cube. So, if I just draw a cross section, there is a strain gauge and there is a cube, right. You can only see one contact if I draw cross section, or you can see both contacts, does not matter. So, on this house fly is sitting, okay, and this is a flexible material, the substrate is flexible. So, if my sensor is sensitive enough, it should bend depending on the weight of a fly, depending on the weight of a fly. So, anyway, this is just to understand the sensitivity of a sensor, right, not actually we are interested in measuring weight of fly, we are interested to use this sensor for the atrial fibrillation. So, and that the grams is about 40 grams and the weight of a housefly is just few milligrams, just few milligrams. This is a dead housefly, not alive. So, do not get confused with that particular thing. The housefly is dead, and then we have stick this housefly on the sensor using a silver paste. Otherwise the housefly will start flying, no, it is not a pet that I can ask sit on the sensor. So, and the image that we have taken is using SEM imaging. So, SEM, we will talk about SEM, we talk about AFM, we will talk about TEM in the following classes. SEM is nothing but scanning electron microscope, TEM is transmission electron microscope, AFM is atomic force microscope, XRD is X-ray diffractogram. So, what are these techniques? These are all characterization techniques, material characterization techniques, right. If you want to see a micro sensor which you cannot see with your microscope, right, can we go for a scanning electron microscope, or you want to know what is the crystalline property of a film that you have deposited, whether it is amorphous, whether it is polycrystalline, whether it is crystalline, then you have to go for TEM, right. Sorry, you have to go for XRD, right, X-ray diffractogram. If you want to know the surface roughness, right, of the film, that once you deposit a film, what is the roughness of the film, you can use atomic force microscopy, right. So, we will look at this characterization techniques in this particular course. Right now, this one is a dead house fly that we have used silver paste to stick it on a flexible force sensor, and we took an SEM image, right. Along with taking a measurement, we have taken the SEM image. So, having said that, let us move further. So, what is the idea? Idea is to develop a catheter, connect a 3D flexible force sensor on the catheter tip, and there are 5 sensors as you can see here, and since it is a strain gauge, we have named SG for strain gauge. So, SG1 to SG5, you can see when you magnify this particular portion, right, and there is this connection through the strain gauges, it comes through the catheter. As you can see, the sensor contacts are right at the tip of the catheter, at the another tip of the catheter, or you can say end of the catheter. And then the idea is that the signals that are generating at the PVI, wherever there is a misfire, the catheter can be placed there and it can start ablating. When it ablates, it should measure the force of the force of the catheter during the ablation, right. Now, if you see here what we have used? We have used a coil as a strain gauge, right. We also did measurement, and if you want to see in detail, please go through this particular work of mine. Is MEMS based flexible force sensor for atrial fibrillation for triaxial catheter contact force measurement. It is published in IEEE Journal of Micro Electromechanical Systems, and you will be able to see in detail how we have performed the analysis. The idea today is to show it to you how you can design this particular force sensor, and then you can always change the design and the pattern to fabricate a better sensor than what we have fabricated in this particular work. Now, if you see this is a rectangular kind of coil. If I ask you that instead of rectangular coil, if I use a circular coil which I have drawn here, which one would be more sensitive? Then you have to understand what kind of mathematical equations you have to see, and you have to go through it to understand the gauge factor. Gauge factor of this particular design would be higher, or this particular design would be higher. When you understand, then you will know which kind of design you should use for particular application. Now, I hope that you all know what is gauge factor, right. Gauge factor is nothing but strain by stress. So, or stress by strain, delta R by R by delta L by L, and the gauge factor for metal is poor compared to gauge factor of semiconductor. So, you need to understand that when you are fabricating a sensor, you need to understand which material you are using and what will be the effect on the gauge factor using that particular material. Now, when you apply, so this is the simulation. Like I always say that no fabrication should be done until you perform a simulation. This is a COMSOL multiphysics, using COMSOL multiphysics we have performed the simulation, and we applied force in different directions. Just a normal force to understand what is the effect of applying force on the sensor, how much sensor will bend, right. How much sensor will bend, and this is very important because we need to understand that if the sensor breaks, then it will not give a correct result. So, we need to understand what is the limit that a sensor can take the force, and that is why the simulation becomes very important. Now, if you see the this force sensor, what you see here? You see that there is a there are 5 strain gauges, right. Then on each strain gauge there is a PDMS bump. Why we are using PDMS bump? Because if I have a strain gauge, let us say like here, right, and if I want to apply pressure, right, I do not know whether it will be here or it will be here or it will be here, right. If I use a bump, right, and if I apply a pressure, right, then it will kind of transmit to all the area, kind of uniform transmission of the force can happen. So, PDMS bump can be used for transmitting the force onto the strain gauge. Now, we have contact electrodes and we have PDMS covered plastic bead, right. So, there is a PDMS covered by plastic bead or plastic bead on which there is a PDMS. The substrate here that you can see is nothing but a plastic bead. So, see this is again a preliminary work. So, preliminary work we are using a plastic bead to understand can we have a 3D MEMS based force sensor, but like I said, can it be actually used in the atrial fibrillation? No. Why? Because the force sensor is sitting at the tip of the catheter, but if you want to perform the experiment, then if you have seen, right, the tip of the catheter that we have designed right now, right, like this, and let us say like this, right, like this. So, this tip will be used for applying RF radio frequency, right, for ablating the tissue. So, if I have a force sensor sitting on the tip, which I have shown here like this, it is very difficult. It is very difficult, and the burning of the tissue, the heat that is generated may cause the force sensor may cause damage to the force sensor. So, we cannot have force sensor at the tip of the catheter as shown here, right. However, the idea was to understand what is the how the force sensor is performing, right, to evaluate the performance of the force sensor. But if I want to have a force sensor, what I will do is I will make a sleeve along this catheter and will make force sensor. So, what I am saying is I will make a sleeve like this, and along the sleeve I will have my force sensors, and here the catheter will sit. So, it will go something like here. Like this, right. My drawing may not be so cool, so do not worry about it. I hope you understand. If you don't understand, just look at me, I will just show it to you what I mean. Yeah. So, this is a catheter, this is a catheter, and what I want is to create a sleeve that can sit on the catheter like this. Now, this sleeve itself, so it is just like a rubber band. If you have seen a rubber band that we put on the hair, right, how the hair is tight with this rubber band, you assume the similar kind of thing, or you can see about a wristband, right, friendship band, wristband, right. So, wristband you put on the hand, correct. Same way this band that is that is having the sensor can be it is a sleeve that you can put on the catheter. So, now when you perform the experiment, if there is a force acting here, a normal force or shear force, you can easily measure it, right. That is what I mean by creating a sleeve instead of putting the sensor at the tip of the catheter. That is not okay, because tip should be used for applying RF ablation, RF frequency or cryo, whatever you want to use for ablating the tissue, but the force sensor should be on the sleeve, or it should be inside the catheter, like what Tachycat, Tachytech and thermocool catheter comes with. So, that is a again there is a fiber optical sensor, there is a spring mechanical sensors, and of course, we have discussed about it yesterday or in the last lecture, but that itself has few limitations, and we have to overcome those limitations by designing this particular sensor. However, so my point is that you can develop a sleeve on which you can have the sensors, array of sensors, and that you can insert on the catheter either inside or outside. So, if you come back to the screen, what we see here is the fabrication process, these two. So, first fabrication is from silicon wafer to a flexible force sensor. Second is from silicon wafer to PDMS bump, right, and then we are taking a plastic bead here and then attaching sensor on each side of the plastic bead, right. See, we are taking a plastic bead and attaching sensor on each side of the plastic bead. So, that makes our sensor ready for measurement. So, now the question lies is how you can design this flexible force sensor, right, how you can design this flexible force sensor. So, let us see in the next slide how can we design this flexible force sensor. So, what is the first step? First step is to take a silicon wafer. Let me draw a little bit smaller so that we can use the entire screen judiciously. We take a silicon wafer. On this silicon wafer, we pour PDMS. Okay. On this PDMS, we have P dot PSS, on which there is a thin layer of silver. This thin layer of silver along with P dot PSS will form our strain gauge. Okay. So, this is our P dot PSS. What is P dot PSS? P dot PSS is a conducting polymer, This is our silver, right. So, what we have? We have silicon, we have PDMS, we have P dot PSS, over which there is a thin layer of silver. Now, on this particular wafer, as you can see here, what was that? Silicon, PDMS, silver on P dot PSS. We have to pattern this, right. We have to pattern to form a strain gauge. So, what we should have? We will spin coat photoresist. Right. After spin coating photoresist, what is the next step? Next step is to soft bake. Right. Soft bake is done at 90 degree centigrade for 1 minute on hot plate, right. Now, after that, what is the next step? We all know, right. Now, we all know how to perform photolithography. It is very easy. Right, silicon, what is next one? PDMS, then we have silver, P dot PSS. On that, what we have? We have photoresist. On photoresist, what is the next step? We have to load the mask, and align the mask, right. Load the mask and align the mask. So, if I load the mask, what kind of mask I have? I have a bright field mask, correct. I have a bright field mask because I want to form a strain gauge. So, the pattern on the mask should be like this, you see 5-inch mask, because our wafer is 4-inch, we have 5-inch mask. The pattern on this, there should be alignment mark. I will talk about alignment mark sometime. What is the importance of alignment mark? When we talk about the, we have already talked, I think, in the section of photolithography, right. So, there is alignment mark, and here we will have our strain gauge. So, in this case, our strain gauge was something like this, right. Right, something like this. So, if I do a cross section, if I take a cross section of this, what will I see? I will see substrate, right, with strain gauge, and this is my silicon, and that is PDMS, correct. This is how I should look at the, this is how the cross section will look like, correct. Now, after loading mask. So, that mask was bright field, we can see clearly, right, bright field mask. After loading mask, what is the next step? Next step is UV exposure, right. Next step is UV exposure. So, UV exposure, cool. Next step would be photoresist developer, right. You have to dip the wafer in photoresist developer. So, when you dip the wafer in photoresist developer, what you get? You have PDMS, then you have P.PSS, right, on which you have photoresist, right. So, what happens to photoresist? Photoresist will get developed in this particular fashion, right. Why? Why it will develop in this particular fashion? Because the area which is not exposed, right, area which is not exposed will become stronger, right, area which is not exposed. You see these blocks, red blocks, that is the area which is not exposed, right. The area below this will not get exposed because the UV cannot pass through these blocks. So, the area which is not exposed in case of positive photoresist will get stronger, right. So, we will have this kind of structure. What is the next step? Next step would be to etch the silver and P.PSS. So, we etch silver and P.PSS. When we etch silver and P.PSS, what we will get? You will get photoresist, this and this is what? Photoresist positive, right. This one would be silver on P.PSS, this would be PDMS and the base would be silicon, correct. After etching P.PSS and silver. What is the next step? Next step would be acetone dip. Why I have to dip the wafer in acetone? You have to dip the wafer in acetone so that you can strip off the photoresist, right. You can strip off the photoresist. So, you have silicon, you have PDMS, right. On that you have P.PSS. When you can now strip off the silver also. After you strip off the photoresist, the silver that was there, you can strip it off. We do not require silver. Silver is just used to it will help in patterning the P dot PSS. Okay. So, what you get? You have strain gauge pattern of P dot PSS on PDMS and PDMS is on silicon. So, of course, when you pour PDMS, after pouring PDMS you have to cure PDMS, right, do not forget it. Pouring PDMS you have to cure PDMS, that is a 125 degree or 120 degree for 15 minutes, depends on the data sheet, manufacturer protocol, right. So, this is what we get, but whereas what about the contact? Contact should be, this is conducting polymer, this is conducting polymer. We want contacts which are metal, right, we want contacts which are metal. So, we have reached this particular stage where we have P dot PSS strain gauge formed on PDMS, but next stage would be to PDMS bump strain gauge and AU contact pairs. Both things we have to go get. First is AU contact pair, and that then next would be the PDMS bump, right, PDMS bump. So, let me have one more slide, so that we can see from here, once we reach this particular stage, right, how can we form gold contact pairs of gold. Okay. So, for that what we will do? We will have PDMS with P dot PSS strain gauge, right. Sorry. P dot PSS PDMS silicon. Now, what we want? We want gold pads on this particular context of the strain gauge, right, gold pads on the contact, gold pads for the contact of the strain gauge. So, we have PDMS, we have silicon, and we have our strain gauge. On this we will deposit chrome gold, all right. So, let us draw chrome gold with some different pattern, chrome gold. Okay, chrome gold is shown like this design. Okay. How we can deposit chrome gold? We can deposit chrome gold with the help of physical vapor deposition. We can use E-beam lithography. We can use E-beam lithography to deposit chrome and gold. Why we need chrome? Chrome is required for better adhesion of gold, right. Chrome is required for better adhesion of gold. So, gold will stick well. Now, after this what is the next step? Next step would be, we all know, right, what is the next step? Next step would be to spin coat photoresist, right. So, we have spin coated positive photoresist. After spin coating photoresist, next step would be pre-bake or soft bake, right, soft bake at 90 degree for 1 minute on hot plate, right. Next step is our favorite step. What is the next step? Next step would be to use mask, right, and expose the wafer. Use mask and expose the wafer. Exposing the wafer with what? Exposing the wafer with UV light. Right. What are we doing now? We have chrome gold, we have PDMS, we have P dot PSS, and on that we have positive photoresist. On positive photoresist we have to load a mask, and mask should be such that it will just protect chrome and gold on the contact pad of the strain gauge, and remaining area we do not need chrome gold, right. So, our mask will look like the one that I have drawn on the screen, correct. So, after loading the mask and aligning the mask, what we will do? We will perform UV exposure, UV exposure. UV exposure. Next step, photoresist developer, right. When we develop photoresist, what we will have? We will have photoresist, we will have photoresist protected only on these two area, right. This is our chrome gold. Correct. Why we have only these two area? Because we are using positive photoresist and the area which is not exposed gets stronger. What is the next step? This is our chrome gold. Next step would be to etch chrome gold, right, to etch chrome gold. So, the area which is protected by photoresist will not get etched, the remaining area will get etched. So, when we perform chrome gold etching, what we will get? We will get strain gauge, chrome gold photoresist, correct. We will have this photoresist, then we will have chrome gold, then we have strain gauge, then we have PDMS, and we have silicon. Next step is easiest step, right, easiest. Acetone dip, dip the wafer in acetone. Acetone is a stripper to your photoresist. When you dip the wafer in acetone, what you will have? You will have a wafer which I am showing it to you right here. You got it? This is what we will have. Now, next step would be to strip off PDMS from silicon, to strip off PDMS from silicon. So, when we will strip off PDMS from silicon, you will get this, right. You will have PDMS with strain gauge, and on the contact with the strain gauge you have chrome gold. So, what we will have? We will have this particular structure, not this particular structure, it is just a bump is not there, bump is not there. So, alternatively what I said, if you do not want to remove PDMS right now, then you can remove it later and keep PDMS on silicon. Alternatively, you can put you do not have to strip off, or you do not have to peel off the PDMS from silicon after this stage, you keep this stage as it is. Okay, we say star, Now, what you have to do? You have to create a PDMS bump, right. We need PDMS bump. For creating PDMS bump, you take silicon wafer, take a silicon wafer, grow oxide, you have silicon wafer, we have grown oxide, oxide is grown using LPCVD or wet oxidation or dry oxidation. You can also sputter oxide, right, but we will grow oxide, oxidize silicon wafer. Next step would be to create a pit. So, to create a pit we have to perform photolithography. So, I will first spin coat positive photoresist. Now, you know, right, what I am doing. So, it is very easy, positive photoresist. Next one would be soft bake. Of course, wherever we are, I am not writing hard bake every time, like for example, after this developing PR developer, right, we before the chrome etchant we had to perform hard bake. We know it, after PR developer this will look like this. After that we have to perform hard bake at 120 degree for 1 minute on hot plate, we know it, right. So, I am assuming that now you guys know when to perform soft bake, when to perform hard bake. So, after photoresist coating we will perform soft bake by loading this wafer on a hot plate, and the temperature should be 90 degree for about 1 minute. Now, after this what we will do? We will take the wafer and we will load the mask. Silicon dioxide, silicon dioxide, right, positive photoresist, we have to protect silicon dioxide all the area except this area, because we want to etch silicon. We have to create a pit, you can see here, right. We have to create a pit after mask. So, now we know what are the things, SiO2, right, layer SiO2, then we have here photoresist, we have a mask, right, which is bright field. After that, next step would be UV exposure. UV exposure. After UV exposure, there is a photoresist developer, photoresist developing step. What we will have? We will have oxidized silicon wafer with photoresist protected in this particular area, right, because we are using positive photoresist. So, area which is not exposed will get stronger, correct. Now, what is the next step? Next step is you dip this wafer in BHF. BHF is SiO2 etchant, SiO2 etchant, right. When you have that, then you have wafer which looks like right. So, you have etched silicon dioxide from the center of the wafer. Now, what is the next step? Next step is silicon etching. Now, silicon etching can be done either using wet etching or dry etching, right. Wet etching we know potassium hydroxide or TMAH, while dry etching is RIE, reactive ion etching or deep reactive ion etching, reactive ion etching or deep reactive ion etching, deep reactive ion etching. When you do that, silicon dioxide act as a mask during silicon etchant, you will get the pit, you will get the pit. Now, on this pit, on this silicon pit, if I pour PDMS on this silicon pit, if I pour PDMS and cure it. So, let us draw PDMS in this particular fashion. In this silicon pit, what I have done? I have poured PDMS and cure it, So, when I pour PDMS and cure it, how it should look like? It will look like a bump and the height of this bump depends on the depth of the pit, right. The height of this bump depends on the pit. So, this is PDMS bump, right. This PDMS bump if I stick it on this silicon, if I stick on this particular bump. So, let me draw it correctly, it becomes perfect. Right, PDMS pump I am sticking on it. Now, after that what I will do is I will peel off this PDMS, I will peel off this PDMS. So, what will I have? PDMS with strain gauge with chrome and gold contact pads and a bump right. So, if you see this particular stage, you will see here PDMS bump on strain gauge with gold contact pads. You are peeling off PDMS and you are getting a flexible force sensor with PDMS bump. You got it? Flexible force sensor with PDMS bump. This is how it is done. So, even it looks very simple and it is really simple, you have to perform photolithography process, right, to get to the level where we can get a flexible force sensor using PDMS. So, when we have a flexible force sensor with PDMS bump, right, flexible sensor is fabricated on PDMS and we have a bump of PDMS on flexible force sensor, then you have a complete sensor realized. Now, you will attach this sensor to the plastic bead, right, a cube, right, that we have discussed on all 5 sides, and once you attach it to all 5 sides of a cube, next step is to characterize that sensor. The characterization of this sensor or calibration of this sensor and using this sensor on gelatin by pressing it on gelatin or in the presence of water, what kind of data we get, we will see in the next module. Till then what you have to see, again just go through this particular class first module, which is your atrial fibrillation, go through videos once again, understand the technique, understand how catheters can be used, and then you look at this particular module and see how we can fabricate a flexible force sensor. So, in the next module we will see how can you use this force sensor and what kind of data you can obtain to understand the performance of the force sensor. Alright, till then you guys take care and I will see you in the next module.